When you look at our beautiful blue planet, it's easy to forget just how fragile it all is. This is the story of its birth. It's a journey through absolute cosmic chaos to figure out how our planet managed to survive when so many others just didn't. Think about it. From relentless solar storms to planet-shattering collisions, most new worlds are destroyed almost as soon as they form. So that's the big question we're tackling here. What makes Earth so special? What sequence of events allowed this one rock to not just survive, but to eventually thrive? Okay, so let's rewind the clock, way back, about 4.6 billion years ago. Earth wasn't a planet. It wasn't even a rock. It was just a cold, dark, sprawling cloud of gas and dust, kind of drifting through the Milky Way. And it's wild to think that all it took was one little nudge, maybe a shockwave from a nearby supernova, to totally disrupt this cloud. Once that happened, gravity just took over. The cloud started collapsing in on itself, and right at its super dense, compressed center, nuclear fusion ignited. And just like that, our sun was born. But the sun's birth wasn't the end of the story. Oh no, it was the beginning of an even more brutal environment. All the leftover material didn't just fall into the star. It got flung outwards, spreading into this thing, a protoplanetary disk. You can just imagine it, a chaotic, violent arena of swirling gas and colliding bits of rock, the birthplace of planets. And right there, in all that chaos, you've got the start of this brutal lottery of planet formation. And let me tell you, this was not a gentle process. It was a cosmic free-for-all where only a lucky few candidates would make it out in one piece. So how do you even get a planet from all this dust? Well, it's kind of like climbing a ladder, step by step. First, tiny little dust grains start sticking together, almost like static cling. As they get bigger, gravity takes over, pulling them into these kilometer-sized chunks called planetesimals. These then smash into each other and merge over and over until you're left with hundreds of planetary embryos, basically moon-sized candidates for becoming a full-fledged planet. And here's the thing you've got to remember. At this point, Earth wasn't special at all. It was just one of hundreds of these embryos, and the odds were seriously stacked against it. Most of them were either swallowed up by bigger bodies, just flung out of the solar system completely, or simply shattered in a collision. So Earth survived round one, but just barely. Its ultimate fate? Well, that came down to two major interventions. One from the biggest planet in our system, and the other from a lost world we now call Theia. First up, Jupiter. Our models show it formed incredibly early, maybe just 1 to 3 million years after the Sun. And its immense gravity didn't just hold on to its own moons. It was the system's architect. It dominated and sculpted the entire protoplanetary disk. One of the coolest theories for how this happened is called the Grand Tack model. It suggests Jupiter first moved inward toward the Sun, acting like a giant cosmic snowplow that cleared out a ton of material from the inner solar system. Now, this was crucial because it starved the region of raw materials, which prevented those massive, hostile super-Earths we see in so many other star systems from forming here. Then, as Saturn formed, its gravity kind of latched on and pulled Jupiter back outward. This whole gravitational dance left us with a system of small, rocky inner planets. So in a very real way, Jupiter's wild journey is why a planet like Earth could even exist. Jupiter's dance made sure a small, rocky planet could exist. But it was another event, a single, violent collision that would decide what kind of planet it would become. This was, without a doubt, the single most important impact in Earth's entire history. A Mars-sized planetary embryo, Theia, slammed into the young Earth. The impact was catastrophic, basically vaporizing the outer layers of both worlds and blasting them into orbit. But from this searing hot disk of molten debris, our moon formed with unbelievable speed. We're talking just a few thousand years. That's nothing, a geological blink of an eye. And the effect was profound. I mean, the difference was night and day, literally. Before the moon, Earth was a mess. Its day might have been only 4 hours long, and its tilt was probably wobbling all over the place, meaning no stable seasons. But after the impact, the moon's gravity acted as this huge stabilizer, slowing our spin down to a 24-hour day and locking our axis at that perfect 23.5-degree tilt that gives us our predictable climate. Okay, so the planet is built. It's got a moon, but the fight's not over, not by a long shot. Now it faced a new, more subtle challenge, actually holding on to the very ingredients for life, its water and its atmosphere. So where did all our water even come from? Well, it looks like it was a mix of two main sources. Some of it was delivered by icy meteorites coming in from the outer solar system, but a huge chunk of it was probably already here, locked away inside minerals deep in the Earth's mantle, and it just seeped out over time. But just having water and air wasn't a guarantee you'd get to keep it. Because the young sun, it was a monster. It was blasting out a solar wind way more powerful than what we see today. And this stream of charged particles is a planetary killer, fully capable of just stripping an atmosphere right off and boiling away its oceans. And if you want a perfect, heartbreaking example of what happens when a planet can't defend itself, you just have to look next door, at Mars. It was smaller, so its core cooled down and solidified way too early. Its protective magnetic field just vanished, and without that shield, the solar wind just scoured the Martian atmosphere away and all its water was lost to space. Mars didn't fail because it never had water, it failed because it couldn't keep it. Earth succeeded where Mars failed thanks to two absolutely critical shields. First, its sheer size. Its mass gave it enough gravity to literally hold on to its atmosphere. And second, its molten iron core, which stayed hot thanks to radioactive decay and all that energy from the Theia impact. That spinning core generates a powerful magnetic field that protects us from the solar wind, even to this day. With its water and atmosphere finally secure, Earth crossed this invisible line. The planet was no longer just a hunk of rock ruled by geology. Matter started to store information. The planet began to remember. It was becoming a stage for life. And life popped up, shockingly fast. The oldest evidence we have, found in the carbon signatures of ancient rocks, dates back to around 3.8 billion years ago. That's not long at all after the planet finally settled down. But life wasn't starting on the surface. No way. The surface was a nightmare of radiation and meteor impacts. The real cradle of life was probably deep, deep underwater, at these hydrothermal vents. These cracks in the ocean provided a stable, protected environment with a constant supply of chemical energy, the perfect spot for simple molecules to start self-replicating. For about 1 billion years, life was pretty simple. But then, around 2.7 billion years ago, cyanobacteria stumbled upon a revolutionary trick: photosynthesis. And its waste product? Oxygen, a gas that was actually toxic to almost everything alive at the time. It caused a mass extinction, sure, but it also completely transformed the planet. It gave us the ozone layer, which shielded the surface and finally allowed complex life to climb out of the sea. So when you put it all together, from a simple cloud of dust to a cosmic demolition derby, to being sculpted by giant planets and defended by an invisible shield, it really hits you. The story of our planet wasn't gentle or guaranteed. It really was an accident, a survivor's tale, balanced perfectly on the knife edge of probability.